Welcome, this is Rob Froney, and I'm here to explain adaptive FIR filters to you. Adaptive FIR filters are basically just an FIR filter that is adjustable, and it's adjusted in this way. Here's the adjustable FIR filter with filter coefficients h sub n of k, and it has an input x and an output d hat of n. And over here there's an input to the whole system, d of n. This is the desired output, and we take and we add this and subtract that to obtain e of n. E of n is the error which we feed into a filter coefficient update algorithm, along with at the input x of n. The output of that is delta h sub n of k here. So what we're going to do is we're going to say n is the iteration number, and every FIR filter has a number of coefficients, and k indexes those. So we could write this. We could write h sub n of k equals, well, let's make it h sub n plus 1 of k equals h sub n of k plus delta h sub n of k. And that's how we'll update the h sub n of k as we add on this guy. Over here, let's put a sum in this box here, because that's summing things. Now the question is, how could we make this filter update algorithm work? Well, let's look at the case for two of coefficients. So let's assume we have two coefficients. And that's because I can only draw two very easily here in 2 dimensions. Let me draw a graph of those. So here's the one axis, here's the other axis. This first axis, or this axis here, would be h sub n of 0, and this one up here would be h sub n of 1. K takes on the values 0 and 1, and capital N will be the number of coefficients, which in our case is 2. So suppose we wanted to try and make this feedback and control system here kind of work. The way we'd want to do that is by making the error here as small in an absolute sense as possible. So I suggest let's minimize e squared of n. The reason we do e squared is it's a lot easier to minimize than the absolute value of e, or we certainly don't want to minimize just e, otherwise e would go to minus infinity. Let's look at a contour plot of e squared here. So suppose this is a contour plot of e squared, and maybe right there is the minimum. This is going down into a hole here. And what happens is we can look at a specific value of e and x and so on will be somewhere on this plot, maybe right here. And if we were right there, what we'd like to do is we would like to take little steps and get down to this minimum here. So we're going to take the method of steepest descent. I'd kind of like to go perpendicular to the contour line here. So I'm going to try and draw a little line in the direction that I'd like to go. And we'd make a step here, and then we'd make another step over here, and eventually, hopefully, we'd end up down in here. So what I'd like to do now is, let's see, I'd like to scroll down on this thing here. So how can I do that? Maybe this box, huh? So what I'd like to do is I'd like to minimize e squared of n by taking the path along minus the gradient. So if we're going to go along minus the gradient here, let's minimize e squared by saying delta h sub n of k will be equal to, I'm going to say negative because we're going minus the direction of the gradient. I'll put in a little mu here for our adjustable step size, and then I want to go proportional to the partial of e squared of n with respect to h sub n of k. And so that would mean that I would be going, each one of these guys for the k equals 0 term, I would be going negative a little bit, like back in this direction, about like that, and the k equals 1 term, I'd be going negative for him. I'd be going a little bit further down than I am on the 0 direction. So actually, if we'd like to kind of do this here, how could we make that work? Let me see if I can move this guy up some here. Maybe this thing here. Let's see. Will that work? Yeah, there we go. Let's see here. I'd like to figure out how does e squared depend on h sub n of k. Whoops, maybe I shouldn't have pulled it up so far because I need to pull that back down to see what's going on here. So if you look at here, e is equal to d minus d hat, so I could write that down. E of n equals d of n minus d hat of n. And d hat of n is the convolution of h of n with x of n. So we could write d hat of n equals the convolution, which is a sum. It's going to be k equals 0 to n minus 1. In general, in our case, n equals 2. And then we'll have h sub n of k times x of n minus k. And if you notice, d of n here doesn't depend on d hat. So let's move this up a little bit. So what I'd like to do is I'd like to figure out what the derivative is here. So the partial of e squared of n with respect to h sub n of k equals 2e of n, differentiating e of n squared, times, using the chain rule, the partial of e of n with respect to hn of k. And let's move this down just a little more. Uh-oh. Maybe I'm at the end of my rope here. Let's go up here and try and make the page continuous. Okay, now maybe I can move it up. No? Guess not. Gonna move it this way? Guess not. Okay, we'll do it up here. Okay, so unfortunately I can't see what I'm doing now. Let's move it down, I guess, and see what we can do. Writing small, maybe down here. So if you notice, the partial of en with respect to hn of k would be the partial minus the partial of this guy, because the partial of en is going to be minus the partial of dn hat, and d doesn't depend on hn of k. So the partial of dn hat would be just there's only one h of hn of k here, and this k goes 0, 1, 2, and so on. And when we take the derivative with respect to hn of 0, we'll just get x of n minus 0. And when we take the derivative with respect to hn of 1, we'll just get x of n minus 1. So in general, this thing down here will be equal to 2 e of n times x of n minus k. Squeeze it in there. Then if we plug this back into this en right here, no, back in up here into the derivative, I get minus, there needs to be a negative sign right here because it's minus dn hat. So it's going to be plus 2 mu e of n, and then x of n minus k. And so that gives us a formula here we can use to run this update algorithm. We'll take en, which we get coming in on the right, and we take x of n minus k, which we have coming in on the left, and we'll plug them into this relationship and get our delta hnk, and then we'll adjust the hn of k's, and hopefully, you know, those things will converge. Now, an option here would be, for this, actually an application would be if I tried to hook up another FIR filter, an unknown one, and put it maybe like this. If I, whoops, if I do this, put an H unknown right here, of K,